Okay, I just got it working. We are doing 2008 number 3. It starts out so easy. They tell you what to plot. I don't think they would make it that easy on next year's test. But anyway, when they tell you what to plot, they don't give you the credit that they give you when they don't tell you what to plot. And you have to figure out how to linearize a nonlinear graph. And you're getting your best fit line. I just went through 2010. You were supposed to do your graph. I told you what to plot. You get your slope of the line. You have to put in your units. This is times 10 to the minus 3. Just keep working. Then they give you a point for getting your units for graphing correctly, etc. Your slope should have been approximately 217. Then they take that slope and they set it equal to G over C as I taught you. The C comes out to 0.045 kilograms per meter. Then we do the graph. You know it reaches terminal velocity. They said speed, so we know it's always positive. It's going from 0 to t. The rest of it was pretty easy. Under the curve, the distance is the area under the curve. For writing that area under the curve, and you had to go from 0 to capital T. Your work not conserved, they gave you a point just for writing out U final. If you wrote U initial plus U final plus work not conserved is equal to U final plus K final, you got a point. For subbing in the values, you got another point. So it wasn't that bad. Okay, you see it better here. You had to have equal increments 0 to 1.2, 0 to 6. Okay, so you're doing 2008, and then we're going to do 2017. Once you get that, you just draw your best fit line, make sure you're indicating your 2 points. You're getting the experimental value of the spring constant. Think of how that slope relates to the experimental value of the spring constant. So they hang this weight and they get the length it's stretched. So think about all your equations for spring. This is a spring, elastic cord, that is a spring. Think about your equations for spring. You only have a couple. You should have your equation sheet out in your pack. And look and see, you only really have a choice of 2 equations for a regular spring. Think of which one you're going to use to get that spring constant. Those are your 2 choices. Think of which one you're using. Just so what are the 2 choices? Can you tell me? Tell me one equation for a spring. Good. Violet, what's the other one? Right. F equals kx is positive or negative, whether you're talking about the work done on the spring or by the spring, but anyways. Okay, so those are your 2 choices. F equals kx and U equals 1/2 kx squared. So, which one of those applies to this data? There's only one that can fit that data. Look at your units. Tori, can you tell me which one fits the data?
F equals kx.
Why?
Because we have the weight and then
Right. You have the weight in newtons. It has to be F equals kx. Okay, so get your spring constant that way. So they made that pretty easy. You didn't. So therefore, F over x is equal to k. Usually you have to fit your slope into some more complicated equation. They made it really simple this time. After that, go on to C. Put your units in on your spring constant. C also isn't too hard. Think what you do when something's falling.
Serious.
should get approximately 25 newtons per meter for your slope. If it's between 23 and 27, you got your point. For any indication using the slope, you got a point. For calculation, 2 points from the straight line. So put in your x's, make them clear. You got a point. For getting the correct slope between 23 and 27, you got a point. Okay, that's good. And go on to C. So in C, remember something's falling. What do we do when something's falling? It comes up again and again.
Sigma FY.
Well, we do sigma Fy if we have some force, but usually just when something's falling, usually it's attached to, it's true when it's attached to a cord and falling, we do sigma Fy, but not in this case with a spring. When you drop a ball, what do we use? It stops and it turns around. So this one isn't, sigma Fy we don't usually use for our spring, right? It's falling, stops and it turns around. Calculate the value of the unknown mass of the object. So you're got to write an equation. What's the most common thing we do when something's falling? What type of equation? Anybody? Something falls.
It'd be like Church-Down equation.
What?
Church-Down equation, right?
Church. Something falls. What is the most common thing we do? What do we do? Conservation of energy. So when you do conservation of energy, you pick 2 points, right? So we want to pick the point when it's released. What should be the other point? When it's released, what should be the other point we pick? Right, when it reaches the bottom. Falls 1.5 meters before stopping and turning around. Since we have that information, and the bottom point is a simpler point. So they tell you that at 1.5 meters, it stops and turns around. That simplifies your conservation of energy equation. You should be able to just plug in that and solve for the mass. You know your K. So you're plugging in your K from part A. This one is worth 3 points. For writing your conservation of energy equation correctly, you get a point. Show me when you have it. Now you have to keep in mind, this is the tricky part of this problem, that it is first falling with no pullback from the spring. Then at some point it starts under the action of the spring. What point does it start under the action of the spring?
1.5 meters.
That's where it stops. Can anyone tell me, when does the spring start to pull back? It starts to pull back before it reaches 1.5, right? At what point does it pull back? If it weren't pulling back already, it wouldn't stop at 1.5. So when does this start to pull back? Samuel, do you know? Jessa, do you know?
Is it mean that gives you like only when it wants fully stretched out or not just like
It's fully stretched out at 1.5. It reaches full point, stops, goes back. But the spring is already pulling on it. Since when?
Maybe whenever it's just throwing balls, it's just
Is it around half the length of the whole stretch?
There's an exact value. You have to know that exact value. They only gave you 2 numbers, right? I mean, which other number did they give you besides 1.5?
Is it at 22 meters?
What's the other number they gave you for this thing? Look at the first page. .6. So it's hanging at 0.6. It's basically the equilibrium point for this thing. So it falls and then it reaches that and then spring kicks in. Okay, so we have our conservation of energy. We're starting with MGH. It stops, so all we have is 1/2 kx squared. The H and the X are not the same thing. The H is how far it's fallen, the X is how far the spring has stretched. Show me when you get your mask. So the height that has changed from hanging here all the way down is 1.5. But the spring has only been stretched 0.6. Sorry, this is 1.5 minus 0.6. It kicks in at 0.6 and then it goes the rest of the way. 1.5 minus 0.6. Now for D, think about what happens at maximum speed. For just writing that down, you get a point. And then after that, we have an equation that just comes up all the time with springs, and you've done a number of times for vertical springs. Whenever you have a vertical spring hanging, you're always writing this next equation at some point. You should get a mass of 0.69. Okay, so for D, write down what you know about maximum speed. It comes up all the time, whether the spring is vertical or horizontal. And then for the rest, consider that this is a vertical spring. What happens at maximum speed?
Acceleration zero.
Right, acceleration is 0, your force is 0, any of those. could write sigma F is equal to 0, acceleration is equal to 0. Whatever it is, you get your point. Now, this is a vertical spring, so when it reaches maximum speed, we know our force is 0. So you should think now you're going to apply that. Your sigma F is 0. Your acceleration is 0. Okay, so now apply that to figure out what the X is. Your force is 0. So your sigma Fy is 0. For every single vertical spring problem, you're at some point, when you get down to the part about forces and accelerations, that's when you're doing your sigma Fy. But it's also the equation that comes up all the time for vertical spring. So what causes that acceleration to be 0? Just, if you need to do your free body diagram,
So, no, the thing was that I had this essentially,
that's right.
but
That's exactly right. Isolate your X.
I thought since we're solving the trying to speed it, that was alright.
Well, they told us maximum speed. But we're not solving for maximum speed, we're just
Oh.
solving for X. So you do your sigma Fy, you have the weight pulling down, you have Kx pulling up. This is true for every single vertical spring. So when they start talking about acceleration, we know this is 0. So we know our Kx minus mg is equal to 0. So K, you isolate your X, you solve for the X. It comes up for every single one. So for correct equation relating gravitational and spring forces, you get your point. For correct numeric substitution of the mass obtained in part C and K obtained in part A, even if you have all the wrong answers, you sub them in, you get your point. Now, when you get that X, that's not the final answer. You get a point for getting the final answer. So we have X is equal to mg over K. So you're going to get approximately what I have here because it depends on what you got for K. But if you had the wrong K and you plugged it in here, you would get full credit. Okay, so plug in whatever you got for your K. Connor, did you get it?
1 second. I got 0.29.
Good. Should be approximately 0.27 meters. And show me if you have your final answer. Okay, so now I don't see. Calculate how far down the object has fallen at the moment it attains its maximum speed. What's the final answer? We just figured out how far did the spring stretch when it attained its final speed. How far did this spring stretch? We did not get how far it was down. What do we have to do to get how far down? Violet, you know?
You subtract.
So it falls, then the spring kicks in, it stretches 0.27 for maximum speed. It's continually increasing in speed. The spring starts to stretch, it continues to increase, and then the spring is pulling back, it slows down.
Do you add the how much it stretches?
You add how much?
You add 1.5 to 0.27.
1.5 is at its final.
Oh,
What do we add? Anybody? Connor, do you know what do we add? Falls down, starts to stretch 0.27.
When you add it to the, what was the 0.6?
Yes, you add it to the 0.6, so you get 0.87. Okay. Let's do another one. We're going to do kind of a hard calculus one. How about that? This next one, they have asked so many times on tests, it is practically their obsession. So I want you to take careful notes in the step-by-step process. It's good for your calculus because it's actually harder. You're going to have to do U to U. And it's actually harder than the U to U I would have on the test. So now, so I'm going to give you other tests in the future that are almost identical to this. And I'm going to say, take out your note of how to go through that step-by-step process because it's always the same. One year, a girl who didn't do well in physics, but she did well in math, she remembered this step-by-step process and she did way better than anyone would have thought because she did well in math. And so she got a question almost identical. And so she went through it very easily because it was the same question every time, just about. They changed a little bit. Okay. So we're going to do number one. Now, we've done ones like this before, but we never had to solve. They said write, but do not solve. So you have to distinguish between write, but do not solve, and solve. Conrad, can you please read number 1?
Yeah. A skier of mass M is skiing down a frictionless hill that makes an angle theta with the horizontal as shown in the diagram. The skier starts from a rest at time t equals 0 and is subject to a velocity-dependent drag force due to air resistance of the form v equals negative bv, where v is the velocity of the skier and the b is the positive constant. Express all algebraic answers in terms of mv, theta, and fundamental constants. A, on the dot below that represents the skier, draw a free body diagram indicating and labeling all the forces that act on the skier while the skier descends the hill. B, write a differential equation that can be used to solve for the velocity of the skier as a function of time. C, determine an expression for the terminal velocity vt of the skier. D, solve the differential equation in part B to determine the velocity of the skier as a function of time, showing all your steps.
Okay, so it starts out so similar to what we've done before. And then the whole thing of writing the differential equation, this is the 3rd time we've done this. So you have done it twice before, but we had something moving, I think it was straight down, but it's the same idea. There is a drag force. So these problems come up when there's drag forces. Okay, so we did 2 where they were moving down and there was a drag force. I don't think we had one on an angle, but it's the same idea. So then you do the whole thing for terminal speed, which we've done before. And then we have to solve what we wrote in B. So when you get to D, I will go through the step-by-step process for it with you. It is a calculus problem of U to U. But let's start out doing your free body diagram. So you're doing your free body diagram, and then whenever you're doing a free body diagram, what's going to come after that? Sigma. Right, it always comes after that. So if you're looking at, hey, I don't see where they said to write the sigma equation, well, then you're missing it, but it's there, so just do it anyway. Then write the differential equation. This is the 3rd time you're doing the exact same thing. Should have 3 vectors in that free body diagram. Sigma Fy, sigma X. You tilt our axes, right? So this VB, when you tilt your axes, VB is sigma Fy, and this would be 0 because it's sigma X. Remember how we tilt our axes?
Wait, so it's going to be easy.
No, he was doing sigma Fy. You should do sigma Fx. You had it right.
Okay.
And then do the next part where you need to write that differential equation. So your free body diagram has three forces. The normal force, the weight, and then this drag force, which you can write with capital F or BV. It's one of the terms they gave. Okay, now we have mg sine theta minus BV is equal to MA. Okay, so that part so far is worth like 6 points, so that's pretty good. Now you have to write your differential equation, which we've done, this is the third time. Hopefully you remember how to do that. I don't think I put it in your pack, but if it's not there, you can just write a note in your pack on how to do that. But you have it in your old problems. I had you look it up last time. Remember I sent you to look it up last time because it was the second time? So on one of the first days, just look in your pack, look at your old problems. It was like, you've done it twice. It's not in your pack, but it's in your old problems. We've done it twice, so you can find it. And show me if you did it.
Oh, I see. What was the one?
Did anyone find it? Yeah. Right. You stick in BVDT for A. It's the third time. It's the same. Now, if they somehow decide we can't keep repeating ourselves, and they had like omega, right? It would be the same idea. If they had alpha, you'd put in the omega dt. There's only so many ways they can do it. If they had one for omega, you'd put in d theta dt. If they had wanted you to write a differential equation to solve for x, then that would be, and they had an equation in b, that would be dx dt. There's only so many choices, but this is the one they've picked almost all the time. Okay, now, let's go on. It says, so far, if you got that far, you would have 7 points. It's really a lot. Okay, now, do your terminal velocity thing. That's the same thing every time, and you get a point for that. Isolate your VT. So just call it. So now this is a different question, right? I mean, we're not working with dV/dt right now. We're working with terminal velocity. So write down what you know about terminal velocity. That's the same thing every time too. Isolate your velocity in the equation. After you do that, go to the calculus. What happens at terminal velocity? Anyone?
Acceleration zero.
Acceleration is zero. It's the same thing every time. You make this zero, you isolate your v. They talk about terminal velocity very often. And so you should just have that right, right away what that means. Your acceleration is zero. You isolate your velocity. Okay, so you should have Vt is equal to mg sine theta over b. Okay, so now we're going back. Let's see you, I want you to write down these steps of the calculus problem. You're separating your variables, integrating both sides, use indicated conditions to solve for c. And then you plug in c. Okay. So let's go back to our original equation where we're doing the u to u. I have mg sine theta minus bv is equal to m dv dt. So we're going to separate our variables. That means you have to put the v with the dv, and if there were a t here, you'd have to put it with the dt. There isn't a t, so you put the constants with the dt. We cross multiply to separate our variables. Everyone write it down? Separate your variables, integrate both sides, use indicated conditions to solve for c, plug in c. Okay. So let's go through separating our variables. You have to cross multiply. To get the BV with the DV, you don't add it to the other side. It has to be in the same term as the DV. So how do we get this in the same term? We cross multiply this entire thing. Okay, so then I have to move up the DT. I always move up whatever is here. And I'm going to move down the M. I could keep the M over there. The math is easier. So write it down. I move up the DT and I move down the M. So I have DT over M is equal to, let me move it over here. DV divided by mg sine theta minus BV, okay? I have now the BV with the DV. So you're not adding BV, it won't be with the same term. You have to cross multiply to separate your variables. Now we integrate both sides. So we integrate this side just as a constant dt. We integrate this side, which is not a constant. We're going to have to do u to u. Let's see if you can do that. Let's see you get started. So on this side, it's not hard to integrate that. It's just this is just a constant, like as if you had 1/3 dx or something. This side, you have to do u du on the right. Let's see if you can do that. You're not used to integrating both sides with two different variables. What do I get when I integrate the left side? Can anyone tell me? It's just like if you had dx over 3. What would be the integral of that? M is a constant. It's not like having a variable in the bottom. It's a constant.
Is that real or is like 1/ln?
There's no ln on this side right here. There's no ln. This is a constant. Just like if you have 1/3, what's the integral of 1/3 dx? You gotta know this on the final. What's the integral from 1/3 dx? 1/3 x. So what's the integral of this?
MT.
1 over m, right? T is here. 1 over mt. Okay, now we have a plus c, but we have a plus c on both sides of the equation, and we don't put them on both sides. It's redundant. We put them on one side. So I'm going to put the plus c. here and not on the right side. Okay, now do your U to U. You could put the plus C on either side, it comes out the same in the end. It's just whatever simplifies the math. So on that right side, you're doing U to U. Now you should see that you have something to the power of 1 in the denominator. That means you're going to be using ln. So you have to do U to U and you have to use ln. Do you have U to U? Or do you have to multiply and divide by a constant? Anybody? Do you have U to U? What? Your U is mg sine theta minus bv. What's the du? When we're taking the derivative with respect to v, what's the du? Anyone? What's the du? What's the derivative of this? If I take the derivative with respect to v, what's the derivative? Tori, can you tell me?
I thought mg sine theta v minus half v squared.
Okay, mg sine theta is just a constant. What's the derivative of a constant? You got to know this for the test Wednesday. What's the derivative of a constant? 0. Derivative of x is 1. Derivative of a constant is 0. What's the derivative of minus bv if v is the variable? Minus b. Okay, do we have U to U? No. Okay. So we have to multiply and divide by minus b. So you're multiplying and dividing by negative b. So then let's see, you get your antiderivative. Show me if you have it. This is to the power of 1 in the denominator, and you have to know this for the test Wednesday. I have something to the power of 1 in the denominator. What do I have to use when I get my antiderivative? Tori, what? What function? ln. You have to use ln. You got to know that for the test Wednesday. When you see something to the power of 1 in the denominator, that is ln. Okay, so you have t over m plus c is equal to minus 1 over b ln. Now, we usually use absolute value, but in this case, we know that we're not going to be working with negatives. So we can just use ln mg sine theta.
Whatever hurts use absolute value.
No, it's the right thing to do, but you just need to understand at some point that we're only working with the positive for this physics problem, getting velocity, getting our velocity, which is only going rightward, so it's going to be a positive. Okay, now use indicated conditions to solve for C. So plug in the indicated conditions. They tell you what they are. It's written there. What are the indicated conditions? Naomi, can you tell me? What's the indicated conditions? The indicated conditions on these physics problems occur at time 0. Okay, so our indicated conditions are initial conditions. T equals 0. What happens at t equals 0? It's always the same thing usually. What happens?
Is that right?
Right, your t equals 0, your v equals 0. Those are the common indicated conditions. Okay, so plug in 0 for your time, 0 for your v, and solve for c. Now you'd find this hard to believe, but this part on this test was only worth 1 point for taking the differential equation and correctly separating the variables, 1 point for correct integration of both sides, and then 1 point for the final answer. But the final answer is a lot of work. On other tests, they gave you 6 points for this. So, you could have just stopped after your integration and gotten and only missed 1 point. But on other tests, it's not like that. Anyway, let's go through the process. Besides, you need to know how it comes out. It can be on the multiple choice too. Where you're just picking out an answer. Once you get your C, okay, let's go through. In order to pull out, because if you plug in 0 for V, you're going to get ln mg sine theta. And on the left side, you're going to have C. You move up that B, and it's going to be in terms of ln. But we want to pull this out of the ln. So do you remember how you pull something out of ln? Use E. All right, so for both sides, we're going to put both sides to E. Now, you don't always have to use ln in these problems, but you often do. So we're going to put both sides to E. So we get T over M plus C is equal to, I'm going to move up that B first. Wait, I'm going to move up the B so I can avoid having that B there. If I move up the B, I get minus BT over M plus C. So now it's easier for me to take the E to both sides because the idea is to get rid of ln. So I'm going to have E to the minus BT over M plus C is equal to E to the ln mg sine theta minus BV. Okay, now remember, what do we do next?
You put T and B as 0.
Well, we can cancel this, I'm thinking.
Oh, yeah.
We can cancel that. Now you can put them at 0. Minus BT over M plus C is equal to mg sine theta minus BV. Okay, now we have another problem here. We have this C. Okay, so what I'm going to do, and this is what we do every time, I'm going to write this as E to the minus BT over M times E to the C. Remember how, E to the 2 plus 3, we can write as E to the 2 times E to the 3. Okay, so E to the C is just a constant. So I'm basically pulling out the constant. Now, in order to not confuse it with the other C we're solving, we can call it a K. But you could have also just called it a C, but we're solving for our indicated conditions. So I'm going to write this now as K E to the minus BT over M, I could call it C, is equal to mg sine theta minus BV. I just want to point out that K is E to the C. E to some unknown constant is just a constant. Okay, now this seems like a long process, but we do it the same thing every time, so we just memorize it step by step one. You also, it comes out in the multiple choice, you pick up the answer. Okay, now plug in 0 for time, 0 for V, and solve for your K. once you have that K, just plug in 0 for B, 0 for T. Fine. What's e to the 0? Anything to the 0 power is what? 1. We get k is equal to mg sine theta. Okay, now we know what k is, which is our e to the c. So let's go back and plug in our k. So we're going back to here. Plugging in for our k right there. Okay, so now I have mg sine theta e to the minus bt over m is equal to mg sine theta minus bv. Now you isolate your v. Let's see if you can simplify it. They only gave 1 point for this isolation on the v after having, like I said earlier, after having integrated both sides. So move everything over, divide down, see if you can then pull out your greatest common factor. So you see how hard this is? This is a hard calculus problem, but since they're so similar every time, it's not that bad. So we move over our mg sine theta. Yeah, mg sine theta e to the minus bt over m minus mg sine theta is equal to v dividing down minus b. Okay, now you want to pull out your greatest common factor. You want to get rid of that negative in the bottom, so you don't put a negative in the denominator. And then the form you should have is basically how it always comes out. So if you see a drag force on the multiple choice question, and then you're supposed to pick from different things that it's how it's going to come out, you can recognize it. It's always in this form. Show me if you have your final. So be sure you know in your notes where this is, because the next time I'm not going to walk you through it. You're just going to look your notes right down. So your greatest common factor is mg sine theta divided by b. You distribute that negative. Okay, so we have mg sine theta over b. I distribute that negative, and I'm going to rearrange these terms so I get 1 minus e to the minus bt over m is equal to v. Now you can write it as minus e to the minus bt over n plus 1, but it's just written like this. This is how you'll see it on a multiple choice question. Now sometimes they ask you to then plot this. So I want you to we'll make up some numbers and you'll get the general waveform in your calculator. So I want you to plot like 5, 1 minus e to the minus 3x, okay? It's going to have the same waveform as what you have here. So let's plot that in your graphing calculator. Then note where the 5 appears. You can start your window at 0 because we're only working with positive, right? Okay, so you should see a rising function, right? This is our velocity. It's reaching terminal velocity. You should see how it goes up, reaches terminal velocity, okay? Is that what you saw? And where does the 5 appear? What role does the 5 play?
Max.
It's the maximum. So that would be therefore mg sine theta over b. Now, in this case, they didn't ask us to plot velocity. They asked us to do acceleration. So let's look at E. It says, on the axis below, sketch a graph of the acceleration A of the skier as a function of time and indicate the initial value of A. Take downhill as positive. You've got to take the derivative of this. Okay? You're going to have to know how to take the derivative on the test. This is e to the u. So let's say you take the derivative of this. You can do it in the other form you had. But anyway, if you want to distribute that, go back and distribute that mg sine theta over b to take your derivative either way. So let's say you get the derivative. Okay, so you're going to get the derivative of this to get your acceleration. So that is e to the u. You should know how to take derivative of e to the u. You're going to have to know that in 2 days.
Is B constant?
Yes, b is a constant. I'm writing it this way, not as a, this is v. Just in case you find it easier to take the derivative in this form. Now, that's only worth 3 points, but it was worth more than all we did for that math. Show me when you're done. Once you get it, I want you to try to plot that in your calculator by just making up numbers for your constant and your E. And then looking at it in your calculator and drawing that. So we have our derivative of e to the u is e to the u du. You got to know that for the test. Got to know derivative of ln u, derivative of du. Let's see.
Just hits. Image PNG.
That also is not additional negative. So this goes to 0. The first term goes to 0. It's a constant. But then we have e to the u du on the right there. So we have the acceleration is equal to 0. Now you got to know this, okay? For that test, this is a constant. It stays the same. E to the u du, e to the minus bt over m. What's my u? Minus bt over m. What's my du? Minus b over m. Okay, so I have minus b over m. Derivative of e to the u is e to the u du. Now we simplify those b's and we get our acceleration is mg sine theta. We cancel out our b's. We cancel out the negatives over m e to the minus bt over m. Okay? Let's see you plot this. We'll make up numbers. We can cancel out this m. Okay, so we get g sine theta e to the minus bt over m. Let's make up some numbers for your constant. So we're just going to plot like, we'll just say 5e to the minus 3t. Just plot that in your calculator, see what it looks like, draw that waveform. And note what that 5 is. You should see a decaying exponential and you should draw that curve. Now this is how, when you have a drag force reaching terminal velocity, this is what the acceleration is always going to look like. You should see something like this. Do you see that? 5e to the minus 3x. You should be sure to put your negative in. And note what that 5 is on the graph. Did you see this? Where does the 5 show up? Naomi, where's the 5? It's the y-intercept. It's g sine theta. So it's the equivalent of g sine theta. Okay, now, so what do you need to remember on this? When you're reaching terminal velocity, your graph always is going to look like, the velocity graph will always look like this. So if they ask you to draw terminal velocity, just draw that, even if we didn't do all this. What is your acceleration going to look like? It's always going to be concave down reaching 0. This is for any drag force, and the chance you have drag force is 100%. But they may not have the specific question, but it's quite common. So even if you didn't get to your math and they ask you to draw the velocity, you just draw this, you draw this. Okay, you don't get whatever points you get for pointing out that that's g sine theta, but you get like 2 of the 3 points. Now, we did not have to go through the work of taking the derivative. I wanted you to do that to remind you of e to the u du, but I know right away that my acceleration, if this is concave up reaching terminal velocity, my acceleration is going to be concave down reaching 0. But there's another way you can do it in your calculator, so let's do that. Let's go back to what we plotted here of 5, 1 minus e to the minus 3x. And we're going to just have the calculator plot the derivative of this, okay? So I want you to go to your function in your calculator where you graph. So go to your graph. And then I want you to plot, and then you're going to enter in the derivative. So instead of just entering a function to graph, you're entering in. So if you get a little picture in your calculator for your derivative, when you go to y equals the plot, you're just going to do 5, 1 minus e to the minus 3x. And then they ask you for like the derivative at a point. Like they'll have x equals something. You just put x there to show that what we're doing is we're plotting the derivative at all points. This is what we're graphing. So you're going to go to your derivative function. You have to graph the derivative like this. We go math number 8. Math number 8, your derivative function. And then you're entering this in. So you're graphing, you're putting it into your graphing function. Okay, so that was what we graphed just now, right? We're going to graph the derivative of that. So we're going to go math number 8 And then you're entering it. So it's gonna graph the derivative for you, so you don't have to go through all that. And you should see what we got you should see your decaying exponential, good. So what you should see when you have your calculator graph the derivative is that decaying exponential we just worked out with EV. Good. Okay, good. That's what you get. So you can always graph a derivative of a function. Sometimes it really takes a while, as long as you have the right window. There it is. You see that same decaying exponential? Okay, everybody got it, right? Okay, so in the future, if you are asked to graph a derivative, don't bother taking the derivative, just have your calculator do it. I mean on the physics test. Okay, now, it's 9:46. We can either go on break and then finish at the usual time, 10:30, or you can just go to 10:17 and finish early. Which would you prefer? Oh, let's take a vote. How many of you want to go on break? You sure? And how many of you want to finish early? Okay. All right, let's just keep going. This saves me having to get that video working the second time. Okay. So we did one. We did, that took us forever, but the next time, it presumably won't take so long. So we still have one more. All we've done is 2. Oh my gosh. So now let's do 2008, number 2. Okay, Naomi, can you please read?
The horizontal uniform rod shown above has length 0.6 meters and mass of 2 kilograms. The left end of the rod is attached to a vertical support by a frictional hinge that allows the rod to swing up or down. The right end of the rod is supported by a cord that makes an angle of 30 degrees with the rod. The spring scale of the variable mass measures the tension in the cord. A 0.5 kilogram block is attached to the right end of the rod. On the diagram below, draw the A and label vector to represent all the forces acting on the rod. Show each force vector originating at its point of application. Calculate the reading on the spring scale. See the rotational inertia of the rod its center is 1/12 in L squared, where N is the mass of the rod and L is the length. Calculate the rotational inertia of the rod block system about the hinge. If the cord that supports the rod is cut near the end of the rod, calculate the initial angular acceleration of the rod block system about the hinge.
Vicky, why don't you read that over to yourself? Look it over.
What's a spring scale?
That means usual bathroom scale.
Oh, so
It's a
it
spring,
measures
like
how
not, it's
much-
not a digital scale, it's a spring scale.
Okay, I thought it was like a spring, like it's in like.
Well, there's a spring inside the scale.
Oh, okay.
So on the diagram, you're just putting in your vectors. Now, this should look familiar to you for certain types of problems we did not all that long ago. Do you remember? Does this remind you of anything? Yeah, it's just like that. This is an equilibrium problem. So pull up your pack to the page for equilibrium and beam problems. The only type of equilibrium problems they usually ask are beam problems. So as soon as you see something that looks like a beam, you're going to go through that step-by-step process. Calculate the reading on the spring scale. Well, you might not know how to do that, but hey, you've seen that beam, and so just go through that step-by-step process. What variable are they asking you? What variable is that for reading on the spring scale? Tension. They're asking you the tension. So you're just going through this equilibrium problem, solving for T. Now, in every equilibrium problem, you're writing that sigma torque equation. You may not have to write sigma fx or sigma fy. You may or may not, but you always have to do sigma torque. Now, I even have the vectors for you in the pack. You have the force on the hinge. So you should have drawn your three vectors just as I have in the pack. I called it R. They're calling it a hinge, so they didn't give us anything we have to call it. But with that hinge, I'm just going to call it H. You could call it R. It doesn't really matter. And then you have T. And then you have the weight. And then you have this little weight hanging here. Okay? So there were 4 vectors. That was worth 4 points. Okay, now let's see you write what you need to write to isolate that t. So you got to write that sigma torque equation. It's almost identical to the one I have in your pack. Isolate your t and then plug in and solve. Show me when you have your tension.
Is the hinge in the equation too?
In your sigma torque equation.
Yeah.
So if you look at that sigma torque equation, we make the origin at the hinge to get rid of that variable in your sigma torque equation, which makes it possible for us to solve for t. The advantage of the sigma torque equation is we can get rid of one. We can get rid of one variable. You just plug in and solve once you write that. So it's almost identical, as I said, to what you have in your pack. You don't need your sigma fx or your sigma fy. You know you're always going to need to write your sigma torque. You may or may not need to write sigma fx and sigma fy. So start with writing your sigma torque. For labeling that as tension, like for writing sigma torque is equal to 0, you get a point. So then for writing, okay, so you needed to know, they gave us the length as 0.6 in your pack. I just am calling it L. You can call it L and then sub in later. So I gave you values. So I told you here it's 1.5 meters. The 300 is halfway, which I called L over 2. 6 newtons was at 600 newtons I had here was at 1.5, but then I have TL sine theta. It's the same exact thing. TL sine theta, and then minus the 2 weights. So in the first case, we have the one on the end, which is L, and then we have the one in the middle, which is L over 2, is equal to 0. It's the same equation I gave you. I just rearranged the terms. Now you can cancel out your L's, or you can plug in. They gave you L is 0.6. Solve for your tension. They gave you the angle. When you have it, let me know. You get a point for having correct units on all your answers. So if you don't know something, you're always plugging in later. So if you don't know, if you didn't get something in A or B, just make something up. Make up a number, put units in, because you get a point for plugging it in later. And if you have the wrong answer, they still give you full credit for plugging it in later. So don't ever stop because you didn't get A. Show me when you have your T. I can cancel out my L's if I want, or you could put in the L that they gave you, 0.6. So I get T is equal to mg plus mg over 2, that whole thing divided by sine theta. And you have two different masses, right? You have 0.5 and 2. If you put the L in, that would have been fine. It would have just canceled out. If you put 0.6 in, it would have still canceled out in the end, but there would have been nothing wrong with that. So to have your weights, use 0.5 as the kilograms. So you have 0.5, and then you have, and this one is 2, so 2 divided by 2 cancels. So I can pull out my G too, so I have 0.5. You don't have to pull it out, but that would only leave me 2 kilograms over 2, which would cancel to 1. And sine of 30 is a half. So if I just look at that numerator, I'm getting 1.5 in the numerator. Divided by a half is multiplied by 2, so I get 3. So you should end up with something like 3 times G, approximately 3 times G. Exactly. They're using 2 significant digits. Should come out to approximately 29 newtons. Okay, all we have in that numerator is 1.5. So what I have is G times 1.5 times 2. I bring up that denominator, 1.5 times 2. G times 3. Okay, let's go to the next one. Rotational inertia of a rod about its center is 1/12 ml squared, where m is the mass of the rod and l its length. Calculate the rotational inertia of the rod block system about the hinge. You're just getting your inertia of the system. That's not that hard. They gave you the inertia of the rod block system. So you're just summing those inertias. It's not hard. Sometimes the rotational questions are really hard. This part here isn't that bad. So you're getting the inertia of the system. So the other one is the point mass. Show me if you have your final answer. So you got to get the inertia of the rod, and then you have to get the inertia of the block. You just sum those two together. So they already gave you one equation, so you're just plugging in 1/12 ml squared. You don't get a point for that. That was too easy. Okay, first, what do they mean by that? So if we have a rod with the axis through the middle, okay, that's 1/12 ml squared, but this is an axis through the end. This is where it helps to remember. Okay, so we have a point mass, that one's easy. You should get a point for getting your point mass part right. For writing the inertia of the system, okay, the inertia of the rod plus the inertia of the block, you got a point. But so we know this one is pretty easy. That's going to be our mr squared. But we're not working with an axis through the middle. We're working with an axis through the end. Do you remember what you do for the end? Do you remember the equation? We have a rod with an axis through the middle is 1/12 ml squared. A rod with the axis through the end is 1/3 ml squared. If you remember that, hey, you're home free. If you don't remember it, it's the parallel axis theorem. And for using the parallel axis theorem, you get a point. So if you just go straight to writing 1/3 ml squared, you get your point. But if you don't remember that, you need to remember the parallel axis theorem. It comes up in other problems. And so the parallel axis theorem I have on page 4, icon plus mh squared. So for writing down the parallel axis theorem, you would have gotten a point. We did this one just the other day. So then you sum them, 1/12 ml squared plus ml over 2 quantity squared. We went through all of this, remember? And then we got, it was just the other day we did the same thing. Plus, then we squared that. We got ml squared over 4. We added these two together. Okay, so we got a common denominator. And we added them, and we get 1/3 ml squared. That's where that comes from. We've done that. Okay, so you need to remember the parallel axis theorem. But if you remembered 1/3 ml squared, you did not need to remember it. You get your point for writing it down. So if you got that wrong and you did MR, you just did the 2, you did it incorrectly, you still got, I guess you only got 1 of the 3 points. But it's good to show you generally what you're doing to get your point. Show me if you have your answer. Good. You should get 0.42. So we're adding in 1/3 m, which is 2 kilograms times 0.6 squared, plus 0.5 times 0.6 squared, which gives us 0.42. It gets your units. You get your point for your units in this one. You don't know, make up a number and put in your units. 0.42 kilograms meters squared. Okay, now you can expect that when you see something like this, they're going to cut that cord at some point because they so commonly do that. So in D, they cut the cord. Calculate the initial angular acceleration. Okay, so we have worked with torque, and now we're asked I. Just write down the equation you know that should be relating to this. You get a point for that. Look at what we've already done. We've so far, we calculated our tension using our sigma torque equation. We calculated our I. We're looking for alpha. Just write down the relevant equation to get your point. So they're asking us about alpha. We've done I. for writing your sigma torque is equal to I times alpha, you got a point. Okay? We worked with I, we wrote our torque equation. You can just guess where this is going. Okay, once it's cut, we have no longer tension. We're looking for I. We have two forces acting on it, the weight of the rod and the block. So see if you can write your torque equation now. You have two torques acting, and two weights. Those are the only torques acting. Remember, you've got to have a lever arm when you write your sigma torque equation. You've got to have a force times a lever arm, a force times a lever arm. What's the lever arm for? We have it rotating down. So we have L. So the center of mass is L over 2. And then we have the block on the end, MGL. It was just a matter of plugging in. You have your two torques. They're both going down. They're both moving. We don't have to use any trig. I'll let you go. We'll plug in and we get 21 radians. You get a point for your unit, second squared. I'm not giving you any homework tonight because I want you to study for that final. Okay? You need to study, guys.